start solving.
Uh,
Okay, so speaker Sobhan Seyfaddini, and he will talk about C0 limits of Hamiltonian paths and spectral invariants.
Thank you, and thank you also for the invitation to speak here. I should also thank all of you guys for skipping your after lunch naps and coming to my talk instead. I hope you don't end up napping here. Okay, so no, I'll start by going over some of my notation first. And so as usual, M is going to be a closed connected symplectic manifold, unless I say so. So at some point it will change. And then omega is going to be our symplectic form. If you have a time-dependent smooth Hamiltonian in a symplectic manifold, as you all know, it gives rise to a Hamiltonian flow. And this is my notation, phi th, so it's generated by h. And throughout the talk, I always assume that the time variable takes values in the closed interval 0, 1. So this is what I mean by Hamiltonian path. And p ham of m is my notation for the space of Hamiltonian paths. And ham of m is the group of Hamiltonian diffeomorphisms, which are just the time 1 maps of such paths. So d is going to be a Riemannian distance on m. And now if you have using this distance d, I'm going to define C0 distance on ham. So first say you've got a single Hamiltonian diffeomorphism phi, then I'm going to define its C0 distance to be the maximum distance between x, there you go, distance between x and phi of x as x ranges over the manifold. And so that's just the standard C0 distance. Now if you've got two diffeomorphisms, phi and psi, then I'm going to define their C0 distance to be the C0 distance between identity and phi inverse psi. So by defining it this way, I've turned it into a left invariant metric. The C0 distance is the left invariant metric on the group of Hamiltonian diffeomorphisms. And say you've got two paths, phi t and psi t. So here I'm not specifying the generating Hamiltonians. Then I denote their C0 distance between two paths by this symbol, d sub C0 superscript path. And that I define to be the maximum distance, maximum C0 distance between the Hamiltonian diffeomorphisms that are in the paths. You know, there's nothing special about Hamiltonian diffeomorphisms. You could define C0 distance on homeomorphisms in this way. So C0 topology on ham is the topology induced by this distance, and C0 topology on p ham, or space of Hamiltonian paths, is the topology induced by this distance. So before I start talking about spectral invariants, I'll say a few words about C0 symplectic topology. So, at least from my point of view, C0 symplectic topology is basically study of C0 rigidity phenomena in symplectic geometry. And I'll tell you what I mean by giving you an example. Perhaps one of the best examples I could give you is the well-known Gromov-Ilya-Aschburgh theorem, which says, so suppose you've got a, can you guys see here? Suppose you've got a sequence of symplectomorphisms. And say phi i's converge in C0 topology to a map phi. So, you know, a priori you don't know if phi is smooth because this is C0 convergence, so in fact it could be a homeomorphism and not smooth. What the rigidity theorem tells you is that if phi is a diffeomorphism, then phi is in fact a symplectomorphism. So if you didn't know this theorem, this should come to you as a bit of a surprise, because being a symplectomorphism is a condition on the first derivatives of the map. And what this theorem is saying is that this condition on the first derivatives survives under C0 limits. And that's a surprising statement. And this is what C0 symplectic topology is about, you know, finding constructions or properties in symplectic geometry that somehow survive under C0 limits. And there is plenty of those. And this is a fine example. Okay, so with that said, I'll now introduce spectral invariants. So maybe I'll cut this board in half. So spectral invariants. Okay, so what spectral invariants are, so say you've got a time-dependent Hamiltonian again, a smooth Hamiltonian, then its spectral invariants are a collection of real numbers, is a set of real numbers denoted by the symbol rho of h semicolon a. I'll tell you what these are. So these are real numbers, and they're indexed by the quantum cohomology of the manifold. Non-zero elements in there. Okay, so these are dynamical invariants of Hamiltonians, and they seem to contain dynamical data about the behavior of the flows. And they've had many interesting applications in symplectic geometry, so I'll just mention a couple, and I'll probably talk about these near the end of the talk. So one of them is a construction of a norm called the gamma norm on Ham. So this is a conjugation invariant norm, and it bounds the Hofer norm from below. So this way you get a whole lot of applications to Hofer geometry as well. So this was constructed through the work of Viterbo, O, and Schwartz, whose name I can't remember how to spell. That's good? Okay, thanks. And another application is construction of, so these are just two of the applications, Calabi quasimorphisms, which you might have heard of, by Entov and Poltrovich. Okay, do I want to say anything else? So, before I define it, maybe I'm going to tell you. So I'll very vaguely say what results I'm aiming for, so that you know what the goal of the talk is. So say, for most of my talk, the quantum cohomology class I'm going to be concerned with is just 1. So say A is 1. Then you could look at so you're fixing the quantum cohomology, and then you get a map from. So if I specify a way to normalize generating Hamiltonians for Hamiltonian flows, then this induces a map on the space of Hamiltonian paths. So from the space of Hamiltonian paths to the real line. And what I'm going to show is that under nice conditions, this is C0 continuous. Under right assumptions. So that's going to be the main theorem of the talk, and the corollary of it, I'm going to show that the spectral norm is C0 continuous on surfaces. So these are the two things I'm aiming for. Okay, so with that said, I'm going to start the definition of spectral invariants. So this is going to be a crash course in Hamiltonian floor theory for the next 10 minutes or so.
It's continuous on higher dimensional things also.
The spectral norm?
Yeah.
Yes. So I think it is. And if there's time, I'll mention another case where I've shown it is C0 continuous. But I haven't been able to prove it's C0 continuous in higher dimensional cases. But that's what I think is the case. So Hamiltonian floor theory, let me just start here. So this is just Morse theory, on some appropriate loop space of our symplectic manifolds. And the loop space I have in mind is, put it down here. So what I have in mind is pairs of loops, loop with a capping disk. So Z is a map from S1 to M, and U is going to be a capping disk for Z. And then you got to mod out by some equivalence relationship, which I won't be needing throughout the talk, so I won't specify it. And so say you've got a non-degenerate smooth Hamiltonian. Then the action, so this is non-degenerate. So what we do in Hamiltonian floor theory is study the Morse theory of its action, the associated action functional. So, and the formula for the action functional is this. So if a pair z comma u is sent to, so first you integrate the Hamiltonian over the loop, and then subtract from that the symplectic area of the loop. Sorry, the capping disk. So my sign conventions are a minus and a minus, and people have different sign conventions. So this is Morse. So the action functional is good enough for Morse theory. So its critical points are, the critical points of the action functional are pairs z comma u, where z is a one periodic orbit of the Hamiltonian flow. So, right, so let me define what the spectrum is right now. So the spectrum of a Hamiltonian is basically the set of its critical values. So the values of the action functionals and at the critical points. Right, and what these spectral invariants will do is give you a nice way of picking out numbers from the spectrum. Okay, so the floor chain complex of a Hamiltonian is generated by the critical points. And in fact, it forms a module over the Novikov ring of the manifold, but other than the symbol lambda, you won't see anything else but the Novikov ring in my talk. So then you have a boundary map which counts gradient trajectories of the action functional. And at least under nice conditions, d squared is 0. So then you could define the homology of this complex, and this is what we call the Hamiltonian floor homology of a Hamiltonian. Okay, so recall that the quantum cohomology of a manifold is just a symplectic manifold is just its singular cohomology with coefficients in the Novikov ring. That's all you need to know about quantum cohomology for today. And one of the most important theorems in floor theory is that there exists a natural isomorphism from quantum cohomology to Hamiltonian floor homology of H. All right, so I'll be using this isomorphism to define spectral invariance in just a couple of minutes. All right, so before I tell you what spectral invariants are, I got to tell you what the action level of a floor chain is. So say you've got a floor chain alpha, then you could write it as a sum of periodic orbits. And these coefficients here, I'm just taking them to be where the coefficients are just rational numbers. And of course, you're only concerned with non-zero ones. And the action level of a floor chain, so I'm going to use the notation lambda sub h of alpha. The action level of a floor chain is the maximum action of the periodic orbits or the critical points that appear in the presentation of alpha. So, right, so this is the action level of a floor chain. Now, right, so if you've got something from Novikov ring, I'll just bring it inside and include it in the capping disk. So it's a sphere, you glue it inside. So then I could just assume these things are just rational numbers. Thanks for pointing that out. So what's important about this action level is, what you should keep in mind is that if you look at action levels below what this lambda h of alpha is, then you will not see the full floor chain alpha in the floor complex. So this is how far you got to go up before you see this chain. Okay, finally, spectral invariants. So take a quantum cohomology class A, and it's got to be non-zero. Okay, so remember, we've got this isomorphism phi, so phi of A is going to represent a floor homology class. Okay, and I will define rho of H A to be equal to the infimum of action levels of floor chains alpha such that the floor homology class of alpha is equal to phi of A, or phi of A. Okay? So once again, the way you should think about it is that this is the minimum action required to see phi of A in floor homology. If you look at action levels below this, you just won't see phi of A. Oh yeah, and then to define all of this, there's like an almost complex structure in the background, and I haven't said anything about it, but you could show that this doesn't depend on the choices you need to make along the way. Also, another question that might come to your mind is that, is this number minus infinity or not? And it is not. So you could show that it's not minus infinity. So it's well defined. Okay, so maybe I should give you one quick example of like how things work out. In general, I think it's, as far as I know, it's not really easy to compute the spectral invariance of a given Hamiltonian. But one case is, say you've got a C infinity small time-independent Hamiltonian. Now it's sufficiently small such that its floor complex is the same as its Morse complex. Then rho of f, so as I said, I will only be concerned with one. Then rho of f1 is minus the minimum of f. Or the minus sign is coming in because of the conventions for the action functional. Okay, so any questions? Now I'll state a few properties of these things. Okay, so these turn out to have a lot of really nice properties. Okay, properties. So the first one I want to mention is a pretty simple one. Oh, no, first one is an important one. They're all important. So you say you've got two Hamiltonians, H and G. Then the difference between the rho of H and rho of G for a fixed quantum cohomology class is always less than equal to L1 infinity norm of H minus G, where the L1 infinity norm of a Hamiltonian is given by this expression. So for each time t, you look at the maximum of ht and subtract from that its minimum, and then integrate that over time. See, it's L infinity in space, L1 in time. So remember that I was assuming H is non-degenerate to define these. Then this inequality allows you to define a spectral invariance for all Hamiltonians. So if H is degenerate, you approximate it by non-degenerate Hamiltonians, and then you get the limit of the spectral invariance of those Hamiltonians. Here's a really simple one, but I'll need it just in a few minutes. So I'll state it. Say you've got a function of time, I'm denoting it by r. Then spectral invariance of, so shift your Hamiltonian by r. Which direction am I shifting it in? Then the spectral invariance of h plus r gets shifted by this value, minus integral of 0 to 1 rt dt. And it's not too hard if you Just look at the definition of the action function. That's where it comes from. Okay. Oh. Oh my God. Bit of an accident. There's a lot of chalk down there. Ah, I see. I bet it happens a lot. Luckily, I won't fall in there. Okay, so here's another one, and this is really the source of a lot of the applications of spectral invariance. That's triangle inequality. Okay, so say you've got two Hamiltonians, H and G. Then I define H sharp G to be the Hamiltonian that generates the flow phi th composed with phi tg. Okay, so the triangle inequality, okay, and let's say you've got two quantum cohomology classes A and B. Then the triangle inequality tells you that rho of H sharp G semicolon A star B, where A star is the quantum product, is less than or equal to rho of HA plus rho of GB. So you get this inequality. And the case I'll be using is this one. So say A is equal to B, and that's equal to 1. So rho of H sharp G semicolon 1 is less than rho of H1 plus rho of G1. Okay, so this is a really nice and important property. And one more property that I want to state is it's called the spectrality property of these invariants. Okay, so here's another property. It's using numbers, now I'm using bullets. So rho of HA, so as I said, these things are supposed to pick numbers from the spectrum, is a number in the spectrum only sometimes if H is non-degenerate. And it's not known. It's conjecture that it's always this is the case, but in general it's not known. So some people call these spectral numbers, and because it is hoped that this condition holds all the time. If your symplectic form is nice enough, then this always holds. Okay, and the last property I want to state is their homotopy invariance property. So say H and G are normalized. And what I mean by normalized is that, so I say a Hamiltonian H is normalized if for each time t its average over the manifold is 0. Okay, so this is the standard normalization procedure. And now suppose that the flow of H is homotopic to flow of G rel endpoints. Then rho of H A is equal to rho of GA. This is the last of the properties I wanted to state. Any questions? Okay, good. So we could start with the research part of the talk. Okay, so for the rest of the talk, I'm going to assume A is 1. Okay, and instead of saying rho of H1, I'll just say rho of H. So here's the question that got me started on this project. Say you've got a sequence of Hamiltonians HI and another one H. And let's assume they're all normalized in the standard fashion. So normalized in this way. Then, and let's suppose that the flow of HI converges in C0 topology to the flow of H. Okay? So the question is limit of rho of hi equal to rho of h. Does this hold? So when I talk about C0 continuity of spectral invariants, I'm talking about C0 continuity with respect to the Hamiltonian flows, not the Hamiltonian itself. So, right, yes?
Just to get a geometric picture in mind a little bit. The class 1, should we think of it as the...
Just the cohomology. You could if you want, but you could also think of it as just the function 1 on, it's a cohomology class. Right? No, you should think of it as the Poincaré dual of the fundamental class of the manifold. Right? So this is a closed manifold, so it's got a nice fundamental class, and you could think of it as the Poincaré dual of that. All right, so if in my definition I was, instead of quantum cohomology, I was using quantum homology, then this would be the minimum action required to see the fundamental class of the manifold in floor homology. Okay. Any other questions? Okay, so the answer is actually no. And there exists a counterexample, which I'll show you. And it's really, I think this is really an enlightening counterexample. So here's a counterexample.
I guess if the support H would be small, the answer is yes.
Yes. No, yeah, I guess you basically got the counterexample. So that's where I got the counterexample. Right. So answer, yeah, this is how you get the counterexample. So I'm going to pick functions like that. So pick your favorite number. Pick a sequence of Hamiltonians fi that are time independent. So fi in C infinity of m. And so I'll pick these to have two conditions. First one is that integral of fi over the manifold is your favorite number c, whatever you want it to be. And the second condition is what Helmut just suggested, and that is I'll take these to be bump functions like this, where the radius, the supportive radius is 1 over I. And what's important is that the support of fi shrinks to a point. Okay? Now note that, but these are not normalized. Right? So, and the condition was that they're normalized. Now, flow of fi, C0 converges to identity. That's because the flow is, is stuck in this small support that's shrinking to a point, so it has to converge to identity. And there exists an inequality that tells you that rho of fi, if the support is displaceable, then rho of fi is less than equal to the displacement energy of the support. And since these supports are shrinking to a point, the displacement energy is converging to 0, so this converges to 0. Right. But as I said, these are not normalized, so now let hi equal to fi minus c, so now it's normalized. And then rho of hi is just rho of fi plus c, so it converges to c. Okay? And that's the counterexample. So what this counterexample tells you is that if you were looking at things with support like this, then you'd get C0 continuity. While when you normalize, then you lose C0 continuity. So what the counterexample is indicating is that this normalization procedure is C0 discontinuous. And if you had a nicer way of normalizing your Hamiltonians, the generating Hamiltonians, then you would actually get C0 continuity, or there would be hope for it. And so for a certain class of Hamiltonian paths that I looked at, there does exist a nice normalization procedure. And so this is the type of Hamiltonian paths I'm going to look at. So let's look at a path phi th such that it fixes the points, all points in some given ball and for all time. then I'll normalize H by what you could probably guess now from the example, by requiring that H at Tp is 0 for all points in this set. Okay, and it turns out that this is a C0 continuous way of normalizing Hamiltonians. In fact, you get better in C0 continuity, and that brings us to the main theorem of the talk.
I see the question. What happens if you have two or more such balls?
I'm sorry?
What happens if you have two or more?
So you're saying the ball is not fixed and like you have Hamiltonians vanishing on different balls?
Okay, I mean if you have another fixed ball, so just and you will have some ambiguity which ball to choose for normalization.
Right.
So you can choose one ball in a collection.
So if you pick, you mean like there's ambiguity to which ball you pick, right? So then it probably won't hold because if you fix the ball, then continuity holds. But if you switch the ball for two different functions, then you're shifting the spectral invariance by some value.
Okay, so it looks like if you have fixed balls that you have chosen, so in fact you can put punctures there, and then you have the same situation as just a manifold without boundary, and you choose normalization of Hofer support Hamiltonian.
Right, but right. So I'm not sure if I understand. So what's the question there then?
Okay,
In principle, he says you cut out this thing, you look at this compactly supported.
Right. Yeah, that's exactly what I'm saying. Right. Compactly. Yeah. So that's right. So if you have a manifold with boundary, then you could do this by requiring things to vanish near the boundary.
So it's the same type of normalization.
Right. You're right. Now you might be tempted to think that you could. Oh, I got to write the theorem first, and then wait. Let me write it, and then we'll discuss it. So here's the theorem. So as I said, you get something better than just C0 continuity. In fact, you get an estimate. So take your ball B in your manifold and fix it, and say H and G vanish on B. Okay, so that's my normalization procedure. Then there exist constants C and delta, positive, and they both depend on the ball B. Now such that if the C0 distance between the flow of F and the flow of G is less than delta, then you get the difference between rho of H and G is less than the constant C times the C0 distance between the paths. Okay, and if you're wondering, this does hold for other quantum cohomology classes too, and it just follows using use the triangle inequality and this and then you could easily get it for other quantum cohomology classes. So two things I wanted to say about it is, first of all, so note that this is a locally Lipschitz estimate, and it's important. It only holds locally. If things are not C0 closed, then you don't get an estimate, because one way to see it is that the right-hand side is always bounded by the diameter of the manifold, while the left-hand side could be unbounded. So it's a local estimate, and it's sharp in the sense that you can't. So there's an example that shows that you can't soup it up to something. So you can't put a power alpha here where alpha is larger than 1. Okay, so this is the best you could do. Okay, any questions about the statement? We'll very quickly sketch an idea of the proof of this. So here's the idea of proof. What am I going to do? So I need a definition here. So here's the definition. Take a number epsilon larger than 0, and say you've got a set U, a proper subset of your symplectic manifold. Then I say U is epsilon shiftable if there exists psi in Ham such that psi shifts the set U by a distance of epsilon, so such that for all x in U, the distance between x and psi of x is larger than epsilon. So what this means is that, if this is your set U, then you psi, what psi does, take U and shift it here by distance of epsilon. And so this is what I call epsilon shiftability. So every displaceable set is, for example, epsilon shiftable for some sufficiently small epsilon. Turns out almost all sets are epsilon shiftable. Okay, so here's a theorem about epsilon shiftable sets or supports of functions. So say support of H. So say you got a Hamiltonian H, and say its support is epsilon shiftable. By, instead of psi, I'm going to say time one map of the flow of K. Now, if the C0 distance between the flow of H and identity is less than epsilon, so if the flow of H is smaller than this number epsilon, then rho of H is less than or equal to rho of K plus rho of K bar. Where K bar, so K bar is the Hamiltonian whose flow is the flow of K to the power minus 1, or inverse of the flow of K. Okay? So I won't say anything about the proof of this. What I'll do is sketch an idea of the proof of the estimate. No, the previous theorem, actually. I won't say anything about the estimate either, using this theorem.
Support of H is
Epsilon shiftable. Right.
Promise I don't see that.
Oh, okay. So here, I'll read it again. So I'm assuming that the support of my Hamiltonian is epsilon shiftable by a given Hamiltonian diffeomorphism. Then if the C0, if the C0 distance between the flow of H and identity is less than epsilon, so epsilon is already given, then rho of H is less than rho of K plus rho of K bar. Okay. So here's a really quick sketch of the idea of the proof. So what I'm going to do is, so this is what I'm going to prove now. What I'll do is, first I'll assume flow of G is just identity. So G is 0. And note that, support of H, just note that it's inside the set M take away B. Right here. So I'm assuming everything vanishes on the ball B, so the support is contained in M take away B. What I'll show is that if the flow of H is C0 is C0 small, then I'll show rho of H is small. Okay, so I won't tell you how to get the estimate. I'll just try to convince you that you do have C0 continuity. Okay, so to do this, right, so pick F, a time-independent Hamiltonian on M, such that F is C infinity small, and critical points of F are all contained in the ball B. Okay, so this tells you that the fixed points of the time one map of the flow of F are all contained in B, and they're exactly just the critical points of F. Right? Now, so phi 1F has no fixed points in M take away B. And M take away B is compact. So if it has no fixed points in there, it shifts the set by a distance of for some sufficiently small epsilon. So phi 1F, epsilon shifts M take away B. And okay, so now if the C0 distance of phi th from identity is less than epsilon, then I'll get that by this theorem here. Then I'll get rho of h is less than rho of f plus rho of f bar. Okay, and I picked f to be C infinity small, so this is small. And in fact, you could show that if the flow of hi is C0 converging to identity, then you could pick fi such that fi is C0 converging to 0. So this tells you how to get C0 continuity. And then to get the estimate, you have to play around a little bit, and it gets a little nasty, but it's not too bad at all. Okay, any questions? Great.
Well, your estimate is quantitative, right? So there is some more work. Right?
Yeah, there is some more. You're right. You're absolutely right. There is some more work to do. But I mean, yeah, it's kind of nasty and boring. Or no, let's not call it boring. Estimates are cool. So I don't want to present it here because it would just take a long time. So by the way, everything I've presented so far. This is from the summer, and I wrote it up, and it's on the archive. If you search for my name, you'll see only one thing with spectral invariants in it, so you'll be able to look up the proof of that. But next, so what I'm going to say next is, now I'm going to talk about a manifold with boundary. This kind of stuff Michael likes. So say M is the unit cotangent bundle the cotangent bundle ball of radius 1. Okay? So, and N is some closed manifold. So this is more recent. In fact, what I'm going to say now is just a few weeks old. And I attended so many talks here by people, and where they attributed their results to the fertile grounds of the Institute. If I remember, Helmut attributed symplectic capacities to a rock in the woods. Right. The woods as a whole. Right, so so I felt quite pressured to do the same thing. And luckily I had just enough time to do something like this. So I'm going to attribute this next result. Unfortunately, it's not going to be as romantic as the woods, so it's the chairs in the Institute, in the dining hall. Okay, so in this setting, the Hamiltonians I'm looking at are all compactly supported in the cotangent ball bundle of radius 1 or any fixed radius. So floor homology is slightly harder to define, but people have done it. And Frauenfelder and Schlenk defined spectral invariants in this case. So and I'll use their notation. So they constructed a spectral invariant. They denote by letter C from C infinity compactly supported Hamiltonians in here. Right. And so their definition is really similar to what I outlined earlier. Some things are even easier because the symplectic form is exact here, so things get easier. And what's important here, so note that these Hamiltonians do satisfy the condition I want for that theorem to hold. And so you automatically get at least this much C0 continuity. But what's cool about this Hamiltonians is this spectral invariance is that C of H depends only on the time 1 map of the flow of H. So then you get a map C that descends from Hamiltonian paths, in fact, to just a group of Hamiltonian diffeomorphisms. Right, so then the question is this map C0 continuous? Right, and this is different. Like, it doesn't follow automatically from that one. Because there I need to assume, before I get the estimate, I need to assume that the two flows are C0 closed. But here I'm just assuming that, I need to assume that just the endpoints are C0 closed. So the theorem is the spectral invariant C is C0 continuous. And I haven't, so I'm going to say this next part is 90%. I'm pretty sure, but I haven't really checked it, so that's why I'm going to say 90%. Or I haven't checked all the details. I'm sure you get estimates like this. Okay, so if phi and psi are sufficiently C0 close. Okay, so then you get that this map is also C0 continuous. So this is theorem 3. Do I want to say anything? So the proof of this is slightly different. But the idea is basically the same, and you have to use that epsilon shift trick. So you pick a time-independent Hamiltonian, that epsilon shifts all of this within all of this manifold within the whole cotangent bundle, and then you play around and you get this theorem. Okay. Okay, so we're done with the first half of the talk, the first 2/3 of the talk, and now I'm going to talk about some applications of these theorems. You know what? I'm going to move to this part. Okay, so we've got 3 different metrics or 3 different norms on the group of Hamiltonian diffeomorphisms. One is the C0 norm, another one is the Hofer norm, and the spectral norm, which I'll define right now. So it's really natural to want to compare these and ask what the relation is between them. And that's what I'll do for the rest of the talk.
The spectral invariants we just defined there, they were, of course, defined like sort of mimicking this min-max construction from
Right.
theory, right? Can you say just one word about how is this spectral invariant here defined? Is there some min-max process behind it? Just to
Right. So here's floor homology. So you take your Hamiltonian H that's supported in the unit ball of the unit cotangent ball bundle, and its floor homology is you have to perturb it and do a few things to define its floor homology and do stuff at the infinity. And its floor homology turns out to be the same as that of the whole cotangent bundle, right? Then to define C, so what?
So if you have a positive or negative small autonomous Hamiltonian, but it's maximum or minimum. I've kind of forgotten what the definition of their action functional was in this case. So their action functional, I feel like, for some reason, I feel like their sign conventions were different than the ones I used. Something like the
Right.
minimum or the maximum.
It's exactly that. Right, so if you have, again, a time-independent C-infinity small Hamiltonian, it's exactly that. And so what you do is that, you take the quantum, there's no quantum cohomology going on here.
that's my question. It's a min-max,
Right, it's exactly the same minimax procedure as before.
but over what kind of homology?
So, right, the homology class you could easily define it for is point, right? The homology class of a point, you could easily define it for that one. And then you use point duality to define. So from what I remember, this was defined for a point, and then they had something defined for a point, and then they used duality to take this one, to define this one. Right. Another one is like you could use isomorphism of this isomorphism with Morse homology, and then you could take the right. Oh, that's another one. Maybe that's the way they did it. So they took the Morse homology class of like a maximum, and then they defined it to be the minimum action required to represent that Morse homology class. So I can't remember all the details, but it's really similar to that one. Okay. So, right. So here is Hofer versus spectral versus C0 norms. Okay, so I got to tell you what these norms are first. So the Hofer norm of a Hamiltonian diffeomorphism is defined by this expression. So it's the infimum of L1 infinity norms of all Hamiltonians, where I think I defined L1 infinity norm at some point, where the time one map of the flow of this Hamiltonian is psi. You take infimum over all such Hamiltonians. So the spectral norm of psi is given by so there's two cases. So first let's define it for M being a closed connected symplectic manifold. Then it's given by this expression. You take rho of h, add to that rho of h bar, and then you take again, so then you take infimum over all Hamiltonians whose time one map is psi. Okay? So that's the spectral norm if in M, if M is not closed. If M is closed. Then I got to tell you what it is in the case of cotangent bundle. In the case of a cotangent bundle, it's much easier to define it. Because as I said, these spectral invariants that Fraunhofer and Schlenk constructed, they descend to Ham. So then the spectral norm, you just define it to be C of psi plus C of psi inverse. I mean, you could define it that way, but it just gives you the same thing. Okay, and so what's known about the relation between, as I said before, so all of these norms are conjugation invariants, so they give rise to left invariant metrics and on Ham. And what's known about, so here's one thing I could tell you about these norms is that the spectral norm is always bounded from above by the Hofer norm. Okay, now I'll say a few things about C0 continuity properties of the Hofer norm. This is really subtle, actually. So C0 versus Hofer norm. Okay, so in the case of R2n, so then we're looking at compactly supported Hamiltonian diffeomorphisms of R2n. Then there exists a famous estimate. Let's see what it's called. C0 energy estimate by Helmut. Can this be attributed to the Woods too, or not this one? What's that? That's all of mathematics, perhaps. So here's the estimate. So it's less than or equal to, the Hofer norm can be bounded by a constant c times the diameter 256. Okay, 256 times the diameter of the support of phi times its C0 distance from identity. Oh, you probably can't see what's here, but you know what's there, right? Okay, so in the case of R2n, this really clarifies the picture and answers all the questions you may have. But it does really use the infiniteness of R2n, from what I remember in the proof, right? So if you fix this diameter to be 1, so to be a unit ball, then to get the estimate, you have to look at Hamiltonians that flow outside the ball, and come back inside at time 1. Okay, if M is compact, then no such estimate. And it is believed that In fact, in all known cases, the Hofer norm is C0 discontinuous. So for example, on S2, you could construct, there exists phi I, which C0 converge to identity, and their Hofer norm diverges to infinity. Or for the disk. All you got to do is take things with large Calabi invariant, and the Hofer norm is always bounded below by the Calabi invariant. So that's what gives it to you. For the disk and for the two-sphere, you use the Calabi quasimorphisms. Okay. So it looks like people seem to think that on closed manifolds, the Hofer norm is always C0 discontinuous. But there's still a lot of interesting questions. And people have thought about it. So one person is Frédéric Leroux. And he formulated this question, which is, I think, a really interesting question. So take a positive number A, and then define E sub A. So this is going to depend on the symplectic manifold. So we define it to be all Hamiltonian diffeomorphisms whose Hofer norm is larger than A. Okay, so Leroux asked is that does E sub A have non-empty C0 interior? Okay, so
To come back to that inequality that you mentioned, because here it depends on the choice of the metric on the manifold. Either a symplectic version, which depends on capacities or whatever, which can define them from symplectic form, or
here it depends on
on the structure of the metric.
Yeah,
Right.
This is the usual metric.
right.
Okay.
Right.
Okay, but if you want the usual metric, that means that it depends on the coordinate system. So if you apply selective market to everything, then C0 norm will change. But Hofer norm apparently will not. So of course you can write infim over all selective market to work, but maybe there is some suggestions capacities.
You don't know? I definitely don't know the answer. Right, I recommend, the proof is really interesting. I can't remember it now, but it's in Helmut's book, and you should take a look at it at some point. Okay, so Leroux asks, does this set have non-empty C0 interior? So, if you take something, can you find a Hamiltonian diffeomorphism with norm larger than phi, larger than A, such that if you C0 perturb it by a small amount, then its Hofer norm still remains large? So Leroux's original question was stated for M equals D2, so the two-dimensional disk. And in that case, this was answered by Entov, Poltorovich, and P. And the answer is yes. And in fact, their methods, so they use Calabi quasimorphisms to answer the question. And in fact, you could show that if this is, the answer is in fact yes for M, any compact surface. Other than S2. So this case is a really nice case that remains open. Okay, so here's the next theorem. I should attribute this to the institute as well. If M is, this is why I started talking about this spectral invariance and cotangent bundles. If M is the unit ball, or of any radius, and the cotangent ball bundle of radius R, then E sub A has non-empty interior. Okay, so how much time do I have left? minus 1 minute. I started a few minutes late. So I won't show a proof of this then. Instead, I'll just state the next theorem. And if you're interested, I could show you the proof. The proof is like basically just follows immediately from this theorem. And you need to know that C is unbounded, and that's also known. Okay, so that's all I'm going to say about the relations between the C0 norm and the Hofer metric. Okay, so I wanted to say something about the, actually, right, I'm doing good with time. So here's the last thing I want to say. So C0 versus spectral norm. Okay, so we saw that the Hofer norm is really C0 discontinuous, but the spectral norm is smaller. So there is some hope for that one. And what I could show was that, so here's the last theorem, takes sigma to be a surface of genus G. Then there exist constants C and delta larger than 0, such that if the C0 distance of phi from identity is less than delta, then you get that the spectral norm of phi can be bounded by C times the C0 distance of phi from identity. Okay, so this is what I was hoping to show, but this is what I could do. 2, so you have to raise this to the power 2 to the power minus 2g minus 1. So the spectral norm on surfaces is also C0 continuous. And I don't have any time to say anything to say about the proof of this or this one. That's it. Thank you.
This is not true for the Hofer metric?
No, on closed surfaces? No. For example, as I said, in the case of the two-sphere, right? Right. Right. Yeah. In fact, I think on all surfaces, I'm sure people have constructed examples where they have shown that it's C0 discontinuous. So what remains open is the Hofer norm semi-continuous? That is unknown. I mean, the fact that the answer to this question is yes, in so many cases, gives you some hope that it might be some sort of semi-continuity might hold.
There's still no cookies.
Oh, yeah. So 25 and it's still cookie time.
Okay, so
Oh.
let's go on.
Thank you very much. This is what I